All right. Hi, good morning. Yes, today we read one of the fairly newer papers. I tried not to give new paper because they tend to be more advanced than the more fundamental papers that we should read. But this paper, even though it's new, it's sort of going in a different direction from what we have done, what people have done in earlier times. So there's not really any prior work to this one. It's a new way of thinking at this work. Thinking at the difference between synchronous and asynchronous I/O, and coming up with a compromise solution which gets the best of both worlds, right? This was published in OSDI 06, and then the paper we read is actually the journal version of it. It won the best paper award in OSDI 06. So, what do you guys think? I thought the paper was really cool, and that's one of the reasons why I wanted to have that, because it's kind of a weird way of looking at the stuff. I mean, weird way of changing the view from where the asynchronous mean. I mean, essentially they're not changing anything. They're just saying that the current APIs try to give synchronicity and asynchronicity based on the application view, not on what can be observed, right? So if I can't observe it, then why bother? So if there's no output from the application, if I can buffer all the output from the application, then I can do whatever I want, right? So since there's no effect possible from the application, I can make sure that I can do whatever I want. I can reorder. I can essentially convert a synchronous program to an asynchronous program if I can prevent things from coming out, right? And of course, that can only happen if I can go through the application and make sure that nothing will ever come out. So they had a paper in SOSP 2005 called Speculator, which essentially does this in a more general sense. So in that, it's like a speculative execution. You want to continue to execute, assuming that you take a certain path, and you want to be able to roll back kind of concept, right? So there they had the notion of, so if you have to wait on something, block on something, you speculatively execute the other path and hoping that you'll take that. If it's not happening, you roll back. So that infrastructure was used in this case, where you know that whenever output comes, you have to maintain the causal links of what caused the output. So you can't let any output go till you're able to do that, right? So that's what they try to do. So I'll start with the reviews that some of you had.
How is it different from branch prediction at the processor level?
The other paper?
Yeah.
It's a higher level. I mean, so you happen at the function level, not at the instruction level. The same idea, right?
Okay.
So the first comment, was fairly long, and two of the issues that he talked about was how far can you extend this, right? So how far can you extend this model? And I think we should have read the speculator paper. And I encourage you to look into the other paper from SOSP 05, right? So you can take it. So all these things depend on how much you have to buffer, right? So if you're producing a lot of output before you have to buffer, then the buffer space becomes an issue. So as long as your application does not, so if you do a speculative execution, but the new execution creates lots of state, then you have to maintain the state. Then at some point, this becomes not so good, right? So even here, if I could, that's what they worry about in terms of commit interval, right? You achieve good performance if you can commit very late into the future, but that means you're collecting a whole bunch of stuff that you have to figure out where to store them, and you have to deal with what happens. So there's a trade-off. So if there's an application which is creating lots of output while before it's forced to flush it, then this approach won't be applicable, right? The other thing he mentioned was the availability of non-volatile RAM. That cache, that idea has been around for a while. It keeps coming in and going out depending on the size of the disk and all those things. So newer, I think they call it hybrid disks, right? The newer hard drives come with a hybrid disk where they have a little bit flash to store some of the. So you get a non-volatile flash storage, and it's useful for energy saving or what have you. So they keep in and out depending on the on the technology cost, right? So how much you want to pay for the hard disk, how much you want to pay for the extra flash RAM, and so on and so forth, right? But I think it's becoming more of a reality now because the cost of the flash is also dropping quite dramatically. So then there's, I don't have your partner, right? So I figured you guys should know the most because that's part of your project, right? For your first project, you are looking at the asynchronous versus synchronous. So this is essentially, in the same space. So one of the common reviews that you guys had was, we don't see much power failure, right? So this system is designed for power failure, right? So if you assume there's no power failure, then you can use asynchronous all the time because asynchronous gives you all the benefits of postponing the outputs. And if there's no power failure, then we can just use asynchronous. We don't have to invent this new stuff, right? Is that the gist of your comments? So it's not your comments?
No, it's not.
So what is your comment? Do you agree with that or do you disagree with that?
We discussed this comment.
Okay.
Yeah.
So did you disagree with your? So I figure this is the comments from you and your partner, right?
Yes.
So do you agree with the comments?
Yeah, maybe like 80% agree.
80%. Okay. So what's the? So let's go with the 80%, 20%, right? So what is the 20% disagreement?
I think asynchronous is better than synchronous.
Okay.
Yeah.
So with respect to this paper, right? So this paper basically says that you don't have to. I mean, you can get the. I mean, if you use their system, right, you can get the performance of asynchronous, but up it with the convenience of synchronous, right? So you don't have to choose. I mean, you can have both. Right? I mean, there's a little bit overhead, like 7% overhead compared to pure asynchronous. But the argument seems to be that you don't have to worry about that because if there is no power failure, then the problem does not even happen, right? So you're trying to solve a problem, even though the approach may be cute and it's good performance and stuff. But if the power failure never happens, then there's no reason for the system at all, right? So it obviously needs for a system, right? So do you agree 80% with the fact that power failures are rare, or do you think that your partner is here too? Sorry to put you on the spot when you walk in, Jen.
Yeah.
So we're discussing your comments, right? So I figured that the comments were written by both of you, right? So your partner only agrees with it 80%, that power failure is not an issue. So do you agree with your comment that if power failure, in the future, power failure is not going to happen, if power failure doesn't happen, then we don't need to worry about the system at all. We can use asynchronous I/O, right? Do you agree with this comment?
Yes.
Do you agree with it 100%? Do you agree with it like fully, right? So he says he only agrees with it 80%, right? So I'm trying to figure out what's the. Can you say something more about this comment? Is that what the system useful for? Actually, you can start, right? You disagree with it, so what do you disagree with this comment?
I think power failure could be an issue, but I think it's not very important. The power failure could be an issue for our system, but maybe it happens rarely or it's not so important.
Yeah, that's a comment, right? So your comment is power failure doesn't happen, so we don't have to worry about this, right? Is that the only reason why you would want to work with the system? I guess anybody can chime in. Is that the reason why you would consider this paper or this technique? You're
You might have other problems than power failure, like server crashes or something. So, which is also the same possibility as in.
Yeah, so I mean, the failure can be for power failure, but can also be for, I mean, any kind of failure would have the same concerns, right? Your operating system may crash or what have you, right? Right? So do you think that the modern systems crash less or crash more or crash so little? So if I change the power failure to generically any crash, right? Could be because of power, could be because of OS failure or whatever, right? In terms of generic crashing, do you believe that modern systems crash or this is not something that we need to worry about? We don't read too many papers actually on failure and modern systems, but just because there's not enough time for that. But yeah.
I think one of the things that causes system failure in today's environment probably clocking between different machines. Screw up the things between the synchronization. Just totally just shut down some nodes. They're very common actually.
You said clocking?
Yeah, in cluster.
So I'm not aware of.
Actually, I had some experience with some cluster, right?
Okay.
And 20 nodes after 1 month, probably one will die. After another month, another one die.
Okay.
After 1 year, probably the 10 left. So.
Yeah, so if that is true, right, so whatever reason they crash, then at some point these things happen, right? And as long as the overhead is not too much, right? So I think most of the file servers that these days would run as asynchronous XFS, I mean the ext3, right? Because the performance difference between synchronous and asynchronous is 100 times, right? So normal servers, you would want to run it in asynchronous mode just because the performance difference is that much, right? But when you have something which, if they can bring it down to about 7% of the asynchronous I/O, then I don't see why you would not want that, right? Because even if the crash is rare, even if it happens once in a month or so, the overhead is small enough that you ought to be able to move forward, right? Some of you have concerns about how much overhead will have for other scenarios that they didn't evaluate, but for the evaluation that they did, which seems to be fairly thorough, it seems to be small enough that you may want to go with that, right? And Ryan had a comment which I don't know if you guys saw this stuff, right? Which is the comment that you hate when you get it from a reviewer. And trust me, when you write papers, you get these kind of reviews that is really gets on you, get behind your, under your skin, which is they did all this analysis for ext3, right? And I'm going to ignore the ext4 is more newer, just because this paper was actually published in 2006, right? So it was probably written in 2005, 2004 timeframe. ext4 did not exist, right? But there are other file systems out there, right? ext3 may not be the most appropriate file system to do this stuff. There are RacerFS, which the reason why I was kind of annoyed was you get these arguments which say, I don't know actually if RacerFS would solve the problem. I have no reason to believe whether it'll solve or not solve the problem. I just think that they should compare it with something, right? Nothing against you, but it's just that you guys will see these kind of reviews and you go like, but I can't possibly test in every file system. I can't possibly look into XFS, JFS, RacerFS, and stuff like that because I need to graduate and stuff, right?
Well, even just like a paragraph where they said, we chose ext3 because that's all anybody ever uses because it's the best and it's the de facto standard, would have been at least a little bit better than just pretending that none of these other file systems even exist.
So let's look at the positive side, right? Yeah, I mean, so the reason why sometimes you don't do that is you don't want to sound like you are defending like a whole bunch of trivial reasons, right? Yes, it's a given that there are other factors which may make this stuff non-viable, right? So, for example, you have to then argue why the hardware that you chose was fairly reasonable, right? So, the disk you chose, why Linux, right? I mean, I would have liked it to be in FreeBSD because I think Linux is not exactly ready for prime time. This is 2.4, right? So, 2.4 is not exactly ready for prime time. So, you should have chosen another operating system, right? So, we can not just the file system. We can say if this was done in X, right? Whatever the X is. If it's done in FreeBSD, this problem wouldn't have happened. This is run with UPS running on a system, kind of stuff, right? So rather than find out what other possibilities could have caused problems, which we don't really know, do we actually believe that this approach is tied to ext3, right? Do we believe that, I don't know anything about XFS or JFS or ZFS, right? Is this a file system issue or is it the OS issue? Is it something that is caused by the operating system or is it something that is caused by the file system, right? So what is the role of a file system that you expect, right? If you're using synchronous I/O, I'm not telling you what file system I'm using. I'm using synchronous I/O. What can, let's say, BFS or some file system that we never heard of, right? I can't say ZFS because it exists. XFS exists too, right? YFS, right? So there's a file system. Let's say there's a file system called YFS. I'm not telling you what it is. I'm just saying this machine is running YFS, and you're using synchronous I/O, right? Or you're using asynchronous I/O. Do you expect that file system would perform any differently from ext3, right? So it's possible that the synchronous I/O in YFS compared to ext3 is twice as fast, right? It's possible that the asynchronous I/O in YFS compared to ext3 is twice as fast, right? So the absolute range of the speeds of the synchronous and asynchronous may be different, right? But is there reason to believe that the differential between these two, between the synchronous and asynchronous, would be different? And do we believe that whatever technique they're talking about would not work in YFS as opposed to ext3? Does that make sense? Because if you don't believe that, this is fine, right? If they use something in ext3 which is specific to ext3 which makes this problem worse than other stuff, then we need to worry about it, right? So for example, if ext3 had a particularly horrendous synchronous I/O, then ext3 should, this is an awful paper, right?
It's an OS issue how you handle the API between the applications and the file system, and it shouldn't really matter. The benefit should be in the concept.
Yeah, I think it's an OS issue and not the issue of, it's the issue of what it means to be synchronous, and I think that's what they're trying to address, right? So we have a concept of synchronous I/O, which is every time you write something has to go to the hard disk, right? I like the way they start the intro, right? Basically, there's a dichotomy between getting good performance and having the reliability, right? So if you assume that synchronous means that everything that you write has to go to disk, then you are bound by the speed that the disk is operating, right? So I can build a different operating system, some of the things we looked at here, which places the blocks close to each other or what have you to make sure that things are faster. But fundamentally, if you do synchronous I/O, things have to go to disk before you can proceed, right? And then the bottleneck is the disk, right? So you can avoid the seeks, but you have to still do that, right? And no one can do that because it's so slow that even in systems, even in Unix, when it has a command called sync, a system call called sync, does not actually wait till everything is synced all the way to disk, right? So even if you do a sync, it's only synced to the disk cache. It's never sent all the way to the disk. You could never make sure that whatever you write goes all the way into the disk and it comes back to you, right? And this is a real problem when you're trying to build a database server, because when you build a database system, you want the database model is when you commit something, it's persistent, right? And all the operating system will let you do is when you commit something, when you do a sync, it's committed to the disk buffer, which is not stable, right? So you have this issue of something that is imposed by the operating system. So I don't really believe that any file system would have changed that fundamental dynamics, right?
The only reason I thought it might would be because depending on the actual difference between speed and synchronous and asynchronous. Okay, 2 orders of magnitude seems like a lot, and I don't know if it's for all file systems 2 orders of magnitude.
So how would you make the file system ignoring ext3, right? No, let's think through that, right? How would you? So what is the best performance you can get? Under what circumstances would you get the best performance out of file system? The other way, under what circumstances would you get the worst performance in a file system in this context? Under what circumstances would the performance be really horrendous when you do synchronous I/O? Random writes which are sunk all the way to the disk, right? So random writes where you have random seeks all over the place to make everything go into disk would be the worst case, right? And the best case would be if everything is buffered, right? If everything is buffered, nothing goes to the disk, right? So I don't know. I can't define whether 100 is the good number, right? But the better you do in terms of buffering stuff, you're going to make the differential larger, right? If I assume that for a certain amount of random writes, that the time to write to the disk is fixed. I mean, I can't modify the disk. I can't make the disk go any faster, right? So I could only do the cylinder groups and all those things to make the things slightly faster, I mean, LFS or something, right? But other than that, you didn't specify LFS, and I think LFS might make things better because it can log things. And actually, they use this LFS ideas under the hood, right? But the asynchronous stuff, I don't see any operating system any other file system would actually make it worse than what they have. I mean, it could be better. I mean, it's easier to see how you can cache stuff, but it's kind of hard. You can't improve the performance when I have to write to the disk, right? That's stuck with it, right? So yeah, it's a valid point, but it's always frustrating when you see those comments and you go like, oh yeah, I know, but those are good ideas because I want you to think through stuff like this, right? Because that's essentially what we're trying to do, right? How likely do you think this idea would be in your next your favorite operating system, right? In Linux, right? How likely are you to see this in Linux? Not a scientific, but your gut feeling of how likely do you think it will be in your next version of Linux?
Well, considering it was released in 2006 and it's not there.
Considering this is running 2.4, not in 2.6, right? So even if you wanted to, you would have to do this in 2.6, right? So you have to see what changed in the kernel. So you have to first port speculator to 2.6. You have to port all this to 2.6, right? Because I think there's a significant difference between 2.4 and 2.6. So you can't just take the old code and put it into a new one, right? Yeah, so considering that 2 years has passed, and considering that he actually works at Microsoft Research now, it's not likely, right? I mean, I think it's unlikely for anybody to go and do this in 2.6 kernel to put it into 2.6 kernel. And none of us would want to do that either because you will get nothing out of it. I mean, other than do stuff, right? So essentially, these ideas are going to die in its current form unless he incorporates that into some of the Microsoft stuff, right? But we want to see whether we can learn something which can possibly be applied to some other case, right? So I strongly encourage you to think beyond what was said in the paper, right? I mean, they have a motivation to make sure that XFS, I mean, that you don't think about all this other stuff because their goal is to get the paper published. But your goal is to understand whether this can be incorporated into your knowledge stream. So it's good, right? I didn't see. What was your comment? Sean?
Mine?
Yeah?
Yeah, mine is just the major thing that's keep reminding me is this is a out order execution, something like that.
Mm-hmm.
It doesn't matter what you do. You just do not do harm to other applications.
Mm-hmm.
You just keep doing something instead of idle.
Okay, I think that kind of ties in with what you guys mentioned, right? In terms of the causal ordering, right? That it's only partial ordering using logical clocks and stuff, right? We haven't read the paper yet, but so causal ordering is, you have some way of ordering these events, because when you have 2 or 3 processes trying to write something, you have to define some sort of ordering. We'll see more detail in the future things, right? Do they change the ordering? Do they impose some sort of ordering on the system? Do they describe any sort of things, or what do you think?
I guess we're just kind of unsure of what the relationship was between the speculative code and the file system, how that all worked together. These logical clocks, they really seem to go into that. So.
Yeah, they didn't go into that, but because I don't think that it's actually there. So I think they're not imposing any order, right? They're only imposing the order that you see on the file system writes, right? So if you have 2 applications which are concurrent, and whatever order happens to write, whatever order you see would be preserved, right? They don't actually change the order. They don't actually create ordering. They don't actually make it any better ordering than what the files were being written, right? So if you have 2 applications which are completely doing the wrong thing in terms of the the ordering thing we'll see in the future. So they don't impose anything. Whatever ordering you saw before is what they have to do, right? I think they go through pains to make sure that they don't actually impose any more ordering, because if they impose any more ordering, then you might potentially lose performance, right? So they don't want to change the way things happen. I mean, so if an application is doing something which is not supposed to do, then it'll continue to do what it's not supposed to do. So it'll behave exactly like how your syncopus would have done, even if that might not be what you wanted, right? And they don't get you good, strict performance. But I think in this case you probably like it, right? Because if you do strict performance on a synchronous I/O, you're going to run at the 100 times slower mode, right? You're going to write everything. So if I want to guarantee the performance, I'm running super slow because everything is going to the disk, right? So their system, you have to compare with not with asynchronous. I mean, really with synchronous, right? So if you're running with their system and it's running 100 times faster, give or take the 7%, right? You're not really going to complain, right? So okay, put it the other way. The system is guaranteed to perform as bad as the synchronous I/O, right? They can only do better. So it's still a guarantee, so they're kind of okay, right? I don't think they want to guarantee too much because, yeah.
I guess one comment I forgot to mention is it seems that some database, like the main target of this sort of behavior would be database engines and things like that, and that some of the database engines have their own file systems, if you will. So just using the disk directly. So.
Yeah, so that's a good observation, right? So is the target for this work databases? I mean, they do mention databases. Is the target for this as a file system to build a database on top of, or do you think this will actually be better inside a database?
Better inside the database.
Because I think that if you ever build a database to use synchronous I/O primitives, your performance is going to be so horrendous that you shouldn't be waiting for this, right? I mean, if you believe that 100 times slower thing, so if you're building it on top of a file system and you're doing synchronous I/O, you're going to be 100 times slower, right? Worse yet, when you do a sync in a file system, in a database where you want the things to be flushed, right? They say it's not actually flushed to disk. It only flushes to memory, right? So it's only 10 times slower because sync is not really a sync, which is really a bad idea for databases. So databases have to make sure that things go into the disk all the time. So databases, if you build it on top of a file system and if you use a sync file system call to flush the database, then your database is poorly designed anyway, right? So you don't want to build this on top of a database, but it might actually be useful inside a database to get good performance, right? So I'm going to use the slides from the authors. So Yeah, so the beauty of the work is they don't change anything, right? They rethink the notion of what it means to be synchronous, right? And they try to address that, right? They start off by showing that, like this is probably what you guys found from your course project, right? Asynchronous I/O is a good abstraction because it gives you as good a performance as you can possibly get, because essentially I give up everything, right? I basically issue I/O commands, but I let the system choose when things should go into the. I don't have any expectation on when things should go into disk, which means that I have no guarantee on reliability, right? So if I issue a write, that means that write may or may not have, go all the way to the disk, right? So it can be delayed for indeterminate amount of time, because that's the abstraction of the asynchronous I/O, right? Asynchronous I/O says that at some point this will be returned to disk, but it doesn't really give you. Nobody's waiting for this to happen, so the application could have proceeded and did something and forgotten what it did. There's no issue of ordering because I'm issuing all these commands, right? The only guarantee I get is when somebody can be notified when a write finishes, right? I can change the ordering to make it work for the system. So I make no guarantees on the reliability, no guarantees on the ordering, no guarantees on the durability, because there's no reason why things should be flushed to disk. Even though synchronous I/O in a typical file system does not even give you durability, because you still, because if you do, then you're operating at, you have to disable all the caches, and essentially you're running at 100 times slower mark, right? And I'm not really sure, but I guess that I don't know how it will be for newer disks which have a bigger cache on the disk, right? I don't know how that plays into what performance you get. And ease of programming, right? Essentially, because now you have to issue something, and then you get a notification back at some other point about how things happen. So if you want to make sure reliability is there, you have to keep track of all the pending stuff. So your application becomes complicated, right? Synchronous I/O is superior. Why is it superior? Why is it superior to you? Or do you agree with that it's superior? Yeah.
It provides a better programming model in the sense that the programmer probably assumes that once they call and write, the program data is there, regardless of what happens.
So here's one question, right? Is it a better programming model, or is it a programming model that we teach you in Programming 101 and so on? Yeah?
Well, I guess when you're like asynchronous, the programmer is probably not going to handle the cases where the data is not actually written to disk, but simply in memory. So it seems to. So what role do you think that academia plays in all this stuff? I mean, this is just amusing, right? So, yeah.
It's just more intuitive. When you say something should be done, it gets done in synchronous I/O. But in asynchronous I/O, you say something should be done, and then 100 instructions later, it might still not be done, which is just not an intuitive kind of way that most programmers look at the world.
So my question is, should we teach kids about synchronous I/O at all, right? It is intuitive, right? But how many of you heard of asynchronous I/O in your programming undergraduate classes? You had? Wow, okay. You had to? You had to? In what class? In the.
I guess we talked about it in OS and some.
Oh, okay. No, not OS class, but programming class, right?
I guess I heard about it in Palm, a class on mobile devices.
Okay. Okay. Yeah.
I guess it has a connection with Java multi-threading.
It all goes into the same kind of world, right? If you do asynchronous I/O, it's good to have multiple threads, because you can then have one thread. I mean, you're writing a scheduler, right? You're writing something which keeps track of when things finish and all those things, right? So they're kind of interrelated. You don't have to have threading, but it helps to have something wait up, right? So why I'm asking is this model of, asynchronous I/O is inherently tied to the notion of threads and those kind of program, right? So it's very easy to think of everything as sequential kind of model. Once you have threading, you have the same asynchronicity, and when you add threads and asynchronous I/O, then it becomes much more complicated way you look at it. One of the things that companies like Intel and all are like funding lots of initiatives in schools to teach is to kind of change the mindset of thinking the synchronous is simple to use, right? It is simple because you pay the 100 times cost at upfront, right? So they would like for us to teach more of the threads and all those things, because if you don't cross this barrier, you're stuck with the slower synchronous I/O. You're stuck with the non-threaded program on the programming concepts, and they're sort of in the same kind of stuff. And there's some debate on what we should do to address this problem. Not just here, but in general, make asynchronous I/O sort of easy to do, right? One of the nice things about this work is you don't have to do that. You can still think in synchronous I/O, and things happen for you. So it's a good model, right? Yeah.
Well, synchronous. How bad will it be when we get to SSD hard drives? Because there's not going to be any seek time anymore, right? So.
Yeah. The current set of SSDs don't seem to be all that good, right?
The reason I ask is because Linus has a blog now.
Okay.
Believe it or not. And on the blog, he said that he got one of the new Intel drives, and he said that it's amazing.
It's amazing?
Yeah.
Okay. But some of the stuff I've heard about those, but they're not too happy about.
Right, and that's what he said. He said that he's gotten a lot of them, and most of them are just awful.
Yeah.
But this Intel one is really
Okay. I don't know anything about that stuff, but is that one does that drive have a RAM buffer to the thing? Because some of I haven't kept up with that model, right? But it seems like if you have if you can write directly into the flash with no memory kind of thing, then your performance is not all that good compared to what you have. So I don't know where the bottleneck is in terms of, is it in the right times? You don't have seek, but you have other costs, right? So I don't know how they do, right? So one of the things with the flash is erasing is very expensive, right? Erasing things are very expensive. You don't get to overwrite anything. You have to first erase and then write new context, right? So if you have an old block, if you want to write a new block, you first have to erase it, which is a very slow process, and then you write the new content. So then depending on how the controller is written, this erasing can happen in the background, or I haven't thought through what that means for file system design, because now you don't have the seek cost, but you have the cost of erasing. So how the hard disk works with the application and stuff like that, right? Yeah, that's an interesting question. I don't know how they will play out, right? And again, processors are getting faster and faster, so everything is racing towards each other, away from each other, right? So yeah, the synchronous I/O can be fast. So the way to solve that is to figure out what it means to be synchronous, right? And so if you change what it means to be synchronous, then you can get the best of both worlds. It's only 8% slower than asynchronous I/O. It guarantees the same kind of stuff that synchronous I/O does. They don't want to do anything more. They could, they can establish ordering and stuff, because essentially they're running their own. They're maintaining which goes to disk at any time, so they can actually play some games here, but they want to make it just like synchronous I/O, right? And the notion is to the notion of external synchrony, right? So what really happens when you flush the disk, right? When you write something in synchronous I/O mode, when you do this stuff, so you have a cache on your disk, which then sends to the disk, right? You can instruct the writes to go all the way to disk all the time, basically disabling this cache, in which case it becomes horrendously slow, right? But the trend is for these things to get bigger, right? I think the 2 terabyte disk have a 32 meg, which is not that big, because you at least have 8 or 16 megabyte, but hopefully you can have more of this stuff here. This is non-volatile. If you pull the plug, or if the system crashes or whatever, then this may not be returned into the disk. And so if you truly want synchronous the way you imagine synchronous would be, anything you write would have to go here all the way to disk, and till it finishes, you cannot do any of the processing. So you have to wait till all the write finishes, right? And of course, that's very slow. So essentially, you still use this cache. So you're still kind of fudging a little bit because this cache will hold all the stuff. If you don't do that, it becomes 100 times slower, right? But it'll be safe because everything you're kind of guaranteed that they go into the disk. I mean, they have caveats on why it's not necessarily what you really want from a application perspective, but you get to write the stuff, right? They have a little animation to, if you lose power, then this cache, we don't know when it writes, right? So I don't know what happens when you have a OS crash here, if it will flush all the stuff up, So this is, when you have power failure, this is what happens, right? Both of them lose power, so you lose the stuff. If you had an operating system crash, do you think that this would be flushed to disk? Maybe, right? I don't know how the hard disk works. Yeah.
I mean, I'm not sure about hard disk, but some RAID controllers on restart of the system will flush the data in the volatile cache, or non-volatile cache to disk.
Yeah, okay, now if they're non-volatile, right? Yeah, if they're non-volatile, then that's one thing. But if you have volatile cache, then it might be returned, right? But then the issue here is there's buffers here, so those wouldn't have been returned. So crash is still not a good thing. So what they really ask is, what is this notion of synchronicity, right? So if you assume synchronicity is what you see from the application, then essentially what you're trying to say is, if I write something, I want it to go to disk. So from this application's viewpoint, I want the guarantee that anything I wrote should be going to the disk, right? That's the notion of asynchronous. Nobody ever articulated it that way, but essentially this application can be sure that whatever it wrote was flushed to disk, right? But their argument is, the application does not know. I mean, how will the application know, right? Application cannot, it doesn't matter what the application knows. It only matters what it tells me as a user, right? So who really needs a guarantee is the user, not the application, right? Even if the application knows that things were not returned, unless it tells me, it doesn't really matter, right? So if I can capture all the messages that it's telling me what is going on, if I can make sure that you will only see it after I've done something that I'm supposed to do, then we can have external synchrony, right? So the model is, we are thinking about this the wrong way because we are trying to make sure that this application will see synchronous behavior. But what we really need to show is, make sure that this application cannot cause any external events in the wrong order, right? So we make sure that this application can never communicate with the rest of the world, or we capture all the communication and then only release them when these things finish, right? So if I do that, then I inherently create asynchronicity between when the application writes something and between when I see it. So I'm collecting all the stuff. So I can essentially change your synchronous program into a synchronous program as long as I can collect all the outputs. So I need to capture all the cases where I'm outputting something. And as long as I don't let you see it, you don't need to know that nothing has been returned, right? The application writes something, it's not returned, but the application says I've returned something, but you don't see it till it's actually returned. So nobody's the wiser, right? So the key is, user observes these operations, but they observe not as application, but they observe as a user. They observe it on the screen. So if nothing comes on the screen, then you don't know what happened, right? You may know it because what you think of the system behaving was not what exactly is happening, right? So you may have some inherent notion of how the output should look like, and in this case, the output may not happen the way you wanted. But for the most part, you won't know because these general purpose operating systems do not guarantee anything about when you should see it. So since you don't have any guarantees, the delay factor, you may not really notice it, so you may be okay, right? I wonder if this will be true for video or multimedia kind of stuff, right? Where you expect output to happen at a certain time duration, which may not be implicit in what the system is showing. They didn't evaluate a movie playing, right? So movie playing, so if you think of some movie being played from the file system, it may be reading some contents and then showing it on the screen, right? So if I'm kind of blocking the showing on the screen for a little bit, right? The timing may be off, but there's no way the file system would know about it. But that's a different problem that they don't really address, right? So they have more graphs to show what the application should block like. So their approach is they give guarantee directly to the user, not to the application, right? This is a neat little idea. So the reason why I like the paper is the idea is sort of neat. The dirtiness comes in the fact that you have to develop all this infrastructure to make sure that this will never happen, right? So you have to develop infrastructure which figures out that when you create an event which is viewed by the user, they have to be captured, right? That means I have to monitor everything where the user can communicate with you. So if a user talks, so I need to keep track of every update. When you said you did it, I have to keep track of those. And I have to keep track of that. So when I hear from the storage system that something has been written to disk, then I can figure out what events can be released, right? So I have to keep track of, I have to taint the output that hasn't been shown to you, right? So I have to internally keep track of all this stuff, and it has to be passed on to other processes. So if I send some output which goes to your application, and you begin to process with that with something, so I have to make sure that anything will happen throughout the system. So if you think you got a message and you print something, you don't print it till. So I think they have some examples on how this happens. So I have to make sure that this happens across the system, right? Because otherwise, it may be, if I just do it on an application basis, then if I send a message to you, that output can actually happen before when I send it to you, and that will violate. So then the user can figure out what's happening, right? So I need to process it throughout the system. So I need to make sure that any mechanism that two applications can talk to each other should be trapped, and I should keep track of this so I can see that print in the right order, right? Does it work for every case in their model, in their system? Are they able to capture every way that you can communicate with another process? Actually, it doesn't. It doesn't work for one particular case. Remember?
Shared memory?
Yeah, shared memory it doesn't work, right? So what's the issue there? It's all related to other stuff we have kind of looked at before, right? So shared memory, you want to create a shared memory between two processes, right? So why aren't you able to figure out when somebody writes and somebody reads, right? The case you want to know is there's a causal ordering if I write something into memory that you read, right? Or vice versa, right? So that way I cause something on you, so I need to taint you, right? So why couldn't they do that? How would you do that if you want to do that? Yeah.
Monitor memory as it's being accessed.
Mm-hmm.
Seems to be more of a hardware issue, something you need to.
Yeah.
You should write a system call or something to write memory, but that would be extremely.
I mean, yeah, you can write a system call which says read memory, write memory. That defeats the whole purpose of having a shared memory, right? If I have a shared memory, I wanted to use it as a pointer, not as system calls. Then the whole thing is kind of messed up. But if I want to do it as so the one way to do that is to play with the permissions, right? Remember, I think we kind of talked a little bit in the memory system, right? So I can change the permissions to make sure that the page becomes non-readable every time, and every time you try to read something, I get a page fault, then I can know exactly what you're trying to do. So if I want to run the system really, then I have to change the shared page into non-shared, every time one of the processes accesses it, then I get the address as a page fault, then I know what you're trying to do, then I can use that to figure out the causal order, right? But it'll be so horrendously slow because in the worst case, every instruction may cause a fault, and you don't want to do that. So they kind of hand wave a solution, but yeah, you don't have hardware support, and it kind of messes the whole thing, right? Because OS is not involved. The notion of the shared memory is the operating system should not be involved. So if the operating system is not involved, they don't get control. They don't know what is going on. That's not a good thing, right? So the examples of a synchronous I/O. So if your program was calling write something, print something, done, and then foo, right? So what you would expect is when write finishes, that buffer is going to disk. Then this write finishes, that buffer is going to disk, and then you print something on the screen. So you expect that this is flushed to disk, this is flushed to disk. You see this on screen, then foo happens, right? This is sort of how you know how the system is working. So this program is running. When the user sees this thing called work done on the screen, then they know that these two previous statements finished, which means that these two things were flushed to disk, which is what you sort of expect, right? Because this is how you monitor what's happening. You cannot monitor these two because these two, there's nothing given to you. But you as a user only knows this when you see this instruction. So they have in the traditional model, you have this nice animation here. So when the process does the write buffer 1, the buffer goes to the kernel, and then it has to be sent to the disk, and the application is blocking at that time, right? And once it got to the disk, then you do the same thing. It goes over here and goes to the disk, and till you're doing this, you can't proceed. So then you don't have to do anything here because this may not be a I/O call at all. But essentially, on the screen you see the work done, right? As long as you can make that work done happen after these things are returned, you're okay, right? And then you get to run foo, right? So that's the key. So once you can figure all this stuff out, so now the good thing is, since you're changing the program to really block on print, which is not how it was done before. Before you were blocked here, you were blocked here. This you never cared before. Now you're changing this system, so this output will be blocked till the write finishes. Since now you have these two writes, buffer 1, buffer 2, then I can do all kind of nice stuff, because since I collected all this stuff, I can internally write them in some good order where I get good performance, right? So if I collect enough stuff here, then maybe I can flush them out all in one go, right? Which is essentially the idea of LFS, right? So if I can collect enough stuff and flush it, so now since I can get these two outputs, I can maybe create a big log and write them all to disk once, right? In fact, I don't even have to wait at print done. All I'm saying is at some point when you finish this and this in that order, first this has to finish and this has to finish, then I have to print this, right? So this particular program, if you do it in a certain fashion, may actually wait for hours, right? If you really make it make the case that these two outputs should be written whenever time is good. So this print work done may never happen because you're holding on to the buffer 1 and buffer 2 and waiting for other stuff so you can flush everything to disk all at once, right? So you don't see this output at all for a long time, and that's the nice thing about the system, right? So you collect. The only thing you have to make sure is you have to write buffer 1 before you write buffer 2, right? That's the semantics of the synchronous I/O. So you're not allowed to change the order, but you're allowed to collect everything and write them all at once, right? That's what their model is. So in their model with the slow animation, so you do these two and they get to the kernel. but nothing ever comes on the screen because you have that text saying print done, but you don't let it go anywhere. So you have to create a dependency graph inside your system where it says print done can only be done if this is done. This can, if these two are done, right, in that order. So once they are done, then the output goes. So it really depends on the speculator paper, which I strongly encourage you to read. Right? So in fact, if you use a speculator, you can actually go past this stuff. You can actually go through foo, because if any of these things fail, you can roll back. They don't do that work here. But if this write or this print fails, right, you can let the whole program go, but then you have to unwind the whole thing if things fail. So you actually get good performance if you use speculator and this system, right? So you see the work done at some point. So that's why they worry a lot about when to do this commit. So essentially, you're doing a commit. So when you print this, you're doing a commit because that means that these two operations have finished before. So they worry about when to commit this stuff, right? So clearly, if you waited for a really long time, you can collect a whole bunch of stuff. You can do the full buffering stuff. But if you collect a whole bunch of stuff, then you have issue reliability, right? Is that true? Do you get a problem with reliability? If you hold this buffer 1 and buffer 2 for a very long time, is that a bad thing or a good thing? They actually worry about this a lot, right? What's the case for holding it for a very long time? Other than performance, like why isn't it such a bad idea to hold it for a very long time? Yeah.
Possibility of a crash might lose the data.
Is that so? Yeah. So possibility of when it crashes, you may lose the data, right? Is it bad in their case? Is losing data really bad in their case? And that's not exactly clear from where they're going, right? So it is bad to lose data, but what happens is you're writing buffer 1, you're writing buffer 2, and you're sending this output, right? So let's say you wrote buffer 1 at 10 o'clock, buffer 2 at 11 o'clock, right? And I don't flush anything at all till midnight, right? And the system crashes at like 10 o'clock or something at night, right? So you lose both of the stuff, right? So what does it mean to lose, right? Because the way the system would have done, you would have never seen the work done on the screen till midnight anyway, right? Because the way they're ordering this stuff, even though you wrote them at 10 o'clock and 11 o'clock in the morning, you were not going to see the work done till it's done, right? So you would have never seen the indication that it was done, right? So if I crashed before then, yes, you didn't see, you lost some data, but you never had confirmation that it was ever returned, right? So is that a bad thing or a good thing, right? Does that make sense? You wrote two things, right? You as a user knew that you wrote two things, but you never got confirmation that you wrote it because you knew that, I mean, I'm exaggerating the time so it kind of becomes obvious, right? So you knew you wrote something at 10 o'clock in the morning, you knew something at 11 o'clock in the morning, but you didn't get any feedback that it was returned because in your code, till work done comes, you don't know, right? So the system might have scheduled to do this work done at 10 o'clock at night, right? So even though you as a user thought you did the write at the right time, you never got confirmation, right? See, the system were to crash before when you actually saw the confirmation, right? In the worst case, the system will look like it's very slow. But since you never got confirmation, they would argue it's not a failure. You have to sort of believe that, right? Because that's inherent to what they're doing. I mean, that's essentially what they're doing, right? They're able to do all the stuff because they're saying, since you didn't get any confirmation, then you can't complain that things didn't go to disk because you never saw the confirmation, right? They'll make sure that you'll never see confirmation till it's actually returned to disk, right? But since there's no confirmation, you can't really complain that things was lost because nobody ever told you it was written, right? You can only complain the system is slow, not that it was lost. Do you buy that argument? Actually, you have to buy the argument. So what do you think of the argument, right? If you don't buy the argument, then the system is not what you want, right? Yeah.
It ensures correctness, but I guess whether it's appropriate for all applications is another story.
So did they evaluate all the cases where this will be a problem? Can you think of cases where this kind of a behavior would not be acceptable? Have you written a program where you knew things should happen at certain times, even though system perspective, it never gave you any confirmation that it did what it's supposed to do, right? Has there been cases where you know, from your own programming experience, right? Would this be unacceptable in some of the systems that you written? Yeah.
So, like interacting with hardware, like the sound card, if you wanted to capture audio, you have to. I mean, if you never received capture when you issued the request, when a device was, you know, inputting data into the computer, and you never received capture, then it's not really useful to you if the system decides to capture 6 hours after the audio source is fed into the system.
Yeah, so multimedia is one of those things, right? So you don't want to delay. Yeah, so let me rephrase what you said. So essentially, if you start to so let's say the right example, right? Let's say the writing that you're doing is to a sound card, right? So you're playing some music, and I click play, and 2 hours later it plays, right? I never got confirmation saying it was printed, so it's true to what you're supposed to see, except when I say play this music, it plays after 2 hours when I might have gone, right? It's the same for data reading, the same thing, right? So those kind of systems you would know, because here though it's not implicit in anything, right? So though there's no feedback, those systems never gave you a feedback, right? But you expect when you click that record button or play button, it will play right away, right? You don't expect, I mean, you expect that play will be slow because of the system being busy or something, but this is actively deciding that you won't write something because it's buffering something, right? They do kind of like try to discuss this issue, because that's fundamentally what's the problem with this approach, right? So is that a sufficient cause for you to reject this work, or does that bother you at all in this kind of a system? Did they convince you that that's okay? How are they addressing some of these concerns? They are trying to hack something into that, right? As part of the discussion on, I'm sorry?
5-second maximum.
Yeah, they put a 5-second maximum on when they should flush, right? So you won't see it. The example I gave you for hours won't happen. It'll come to you within 5 minutes, and 5 minutes they got from some XFS stuff, right? Yeah, so they like it because they say basically now you are committing based on the output, right? So if I don't see output, I can collect a whole bunch of stuff. So if this print happened after 1,000 writes, then I have created a barrier for 1,000, output-driven barrier, so I get good stuff. But the flip side is then I can potentially make you wait for too long. So they put 5 seconds. So 5 seconds seemed like a fairly decent amount of time. I mean, not too long, right? So in this case, you'll see the output after 5 seconds or so. So you may be okay, right? But that's inherent to this system. The trade-off on when you should force the stuff, right? So if the time is too small, then you lose some of the benefits of their system, right? If the time was 1 second, then you may not be able to collect a whole bunch of stuff. But on the other hand, you won't run into the problem where the output is taking too long, kind of stuff, right? So yeah, so I suspect that you'll come up with that number as you use the system, trying to figure out what's a good match. Yeah.
I'm curious how would you react to synchronization? I mean, if you wanted to say, capture audio and video simultaneously, and at some point the commit for the capture happens, or audio happens at time 1, and the capture for video happens at time 2, then you'd be out of synchronization in that aspect.
Yeah, I don't think this approach works very well with the multimedia kind of stuff that you're talking about, right? Or any kind of sensing kind of stuff.